All right, let's begin. I've got your homework assignments there for assignment 4C. I'll collect your reports in lab today. Group B at 2 o'clock, Group A at 3. We're going to be doing the jet impact lab, and I've handed out the information you need to get ready for that. I'd appreciate it if you have a chance to read through it. Strange that that page 3 is blank like that. I guess it just was an extra space or something. Homework 5A is due on Thursday. So we're not going to be meeting as a class on Thursday. This is really important, so if you're talking right now, you should stop talking and you should listen. Submit the assignment into this folder that says 318 in it. That's our class number. It's going to be in the metal box that's beside my office door, and it needs to be submitted by 11 o'clock on Thursday. So I'll set this out. I'll be here very briefly in the morning on Thursday. I'll set it out probably around like 9 a.m. or so. And so if you want to turn it in before that, you can just give it to me directly. This may be the easiest assignment of the semester, this Chapter 5. It's just 4 problems. They're all based on the continuity equation. So I think that if you sat down, you could probably complete this assignment in 30 minutes, maybe an hour. And so it's due by 11 o'clock on Thursday. The grader's going to pick it up directly from my box and start grading it. The lecture is online for Thursday. I've already posted the link to the lecture on MU Online, so it's available now if you want to watch Thursday's lecture. So don't come here Thursday at 11, but you can submit your assignment by my office door. Any questions about how things are going to go on Thursday? Question about lab today? All right. Well, today we're going to continue talking about information from Chapter 5, and we'll begin with the review. What we talked about last time was Reynolds transport theorem. And here is Reynolds transport theorem. And it was the idea that we're going to be keeping track of a system, where a system is this continually connected mass of particles. It could be gases, it can be liquids, but the system can deform over time, its position can change over time, it can rotate. But the idea of what we're going to be doing is tracking where the system is relative to a control volume. And the control volume is just an imaginary space that's bounded on the outside by control surfaces. And what this Reynolds transport theorem says is that we keep track of the movement of material through the control surfaces, CS, and so this is the transport term. And then we also consider the accumulation of mass over time inside of the control volume. And over time, the mass of the system, if we assume that the mass isn't being created or destroyed, what we did was we set the left-hand side of that equation equal to 0. And so by setting the left-hand side of the equation equal to 0, like is shown here, it says that the rate of accumulation inside the control volume is dictated by the flow in and out through the control surfaces. And so the typical environment that I apply this to is the environment of a tank, like a tank that has a fluid mass accumulating. Oh, there's a marker. And when we were looking at the system, we said that there was some flow into a tank. And so we just drew these imaginary lines, and the water level will either be falling or rising depending on the difference between the flow in and the flow out. And so Reynolds transport theorem is all about the calculation of where the mass is over time. And mass flow rate, m dot, is volumetric flow rate multiplied by the density. And so if we consider that liquid, maybe water, for example, has a density of 1,000 cubic meters, and we know the volumetric flow rate in, the volumetric flow rate, then we can keep track of the change of mass inside the control volume over time. And that's how to say aloud the left-hand side of that equation, dm CV divided by dt. That's the change in mass inside of the control volume over time. And one of the important applications that we're going to use information from Chapter 5 in is when we want to try and use equations that are that were envisioned for the Lagrangian approach. And for example, remember that one of the limitations of Bernoulli's equation is that we're only supposed to apply Bernoulli's equation along a streamline. That's one of the assumptions, is that it will tell you the change in pressure along a streamline as long as it's an inviscid fluid, meaning that it doesn't have any viscosity. It's incompressible, that the flow is steady over time. But along a streamline is not real convenient. We've talked about why all these different streamlines, there's going to be literally billions of streamlines because there's many billions particles and they all have a different path. And so it's more convenient for us to, instead of taking the Lagrangian approach to visualizing flow, sometimes we'll use the Eulerian approach for visualizing flow. And that means that we'll break up our flow environment into cells, and we will say that the properties of the fluid at a certain location, all of the fluid particles inside a certain cell have the same velocity, the same direction, the same pressure. And it's a simplification to be sure, but we can't apply equations like Bernoulli's equation, which were developed for Lagrangian environment, to this Eulerian approach of dividing up the flow field into segments. And so the continuity equation is going to allow us to actually combine the two. The continuity equation will allow us to say that the fluid properties move through the boundaries, and so we're going to take a control volume, like each one of these cells is a control volume, and we're going to look at the flow in and the flow out of all the properties of the fluid. And so we talked about intensive and extensive properties in class last time on Thursday, and how anything that has a fluid property related to mass, like momentum or the mass of the fluid itself, if we look at the accumulation of those properties inside of a cell, then we can know the difference between the in and the out over time. And so this Eulerian approach is going to allow us to combine Bernoulli's equation in a way that we ordinarily wouldn't. And the idea of computational fluid dynamics is to track the pressure, shear forces inside of any kind of a fluid element, whether it's a river. If this could be a river that's getting narrower, for example, we might want to divide the flow field up into pieces to try and understand what's happening to the depth of the flow. Or if it's an enclosed environment, we want to know how the pressure changes over time. And so, just as a little bit more background, one of the purposes that we use the Reynolds transport theorem is just to make it possible for us to relate the Lagrangian equations like Bernoulli's equation into an environment that we want to break up into cells. So let's apply the continuity equation with 3 examples today. That's what we're going to be doing through the entirety of the rest of our class period today. We've got a tank, and we're going to analyze this tank in terms of what's happening inside the control volume. The control volume is what's inside of these exterior control surfaces. So the control surface is the wrapping paper. The control volume is the box that's inside the wrapping paper. And this is a present inside. It's a water tank that we know that the flow in is not equal to the flow out. It's implied by the problem statement. It says, how is the liquid level changing with respect to time? All right. So what we want to know is, what is the change in mass inside of here? And it's a circular tank with a diameter of 0.5 meters. And so that dimension isn't drawn right here, but from one end of the tank to the other, it's circular, has a diameter of 0.5 meters. And so what I'd like you to do is either work individually or with the partner and find out what's the flow rate in compared to the flow rate out, and then the difference between the two will tell you the mass accumulation rate, and then convert that to the velocity, how many meters per second is the liquid level going up or down. And while you get started on that, I'm going to go grab a fresh marker so that I can put the solution on the board. Okay, we start off by looking at the flow in. We know the diameter, or not the diameter, but we know the area of this stream of water that's pouring in. The cross-sectional area of it's 0.0025 meters squared. Mass flow rate, m dot, is density times the volumetric flow rate. And volumetric flow rate is area times velocity. And if you look at the units, even if you didn't remember that formula, you can look at the units and figure that out, because you've got meters squared, and we know volumetric flow rate is cubic meters per second. So if you have meters squared and you also know meters per second, multiply them together and you'll have cubic meters per second. So that gives us the volumetric flow rate, which then we multiply by the density. It's 17.5 kilograms of water per second that's going in through the control surface. Now there's a hole in the tank, and the liquid level is governed by the flow in, but it's also governed by the flow out. And so how much water is flowing out of the tank is known in terms of volume, 0.003 cubic meters per second. Well, that's equivalent to 3 kilograms per second, because we multiply the volumetric flow rate by the density and get the mass flow rate out, 3 kilograms per second. So now the difference between the two, the in minus the out, tells you accumulation. And that's the simplified version of the Reynolds transport theorem, is that the accumulation inside the control volume is just in minus out. So here the 17.5 minus 3 means there's a net increase of 14.5 kilograms per second. So that's the mass flow rate that's accumulating. But ultimately what we're after is to know the velocity that the liquid level is rising. So to know that, we have to switch back into volumetric terms instead of mass flow terms. So here we have the mass flow accumulation of 14.5 kilograms per second. If we convert that back into volumetric flow by dividing by the density, that's 0.0145 cubic meters per second. That's the rate that volume is accumulating inside the control volume. And then the cross-sectional area, you can just imagine that if this was a really big tank, the liquid level would be rising more slowly. And anybody who's filled up a swimming pool before knows how long it takes for the level of the swimming pool to rise. You can't see it. It's so slow, just if it's being filled from a garden hose. So in this case, the diameter of the tank is used to calculate the cross-sectional area, and then velocity of the rise, how quickly the water level is going up, is just the volumetric flow rate divided by the area. So 0.0145 cubic meters per second divided by this cross-sectional area of 0.19635 square meters, and that velocity is 0.0738 meters per second. So it's rising very slowly. Now some of the things that could change over time is if this outlet isn't regulated, like if it's just a hole in the tank, you already know that the higher the liquid level gets, the faster the flow rate out is going to be. So it's possible that over time, that liquid level could rise and rise until finally it reaches equilibrium. Equilibrium means that the flow rate in and the flow rate out are equal. Equilibrium means steady state. So as the liquid level increases, the velocity of that jet that's coming through the orifice could increase as well, unless there's a valve there that's controlling the flow rate. It looks like this is actually an enclosed pipe. It's not like a free jet that's coming out. So it, not pictured, might be some sort of a flow regulation valve. But I'm just telling you that one variation of this type of problem is asking what would be the height of the water when it reaches equilibrium. Because in that kind of a problem, you'd be saying, assume the flow in and the flow out are equal. So you'd need to know what velocity is going to give you the mass flow rate out that is equal to the mass flow rate in. But this is a far simpler problem than that. Here all we needed to do is find out what does the accumulation look like? What's the water level rising at what rate? And there it is. Okay, so any questions for this example? That case that I was just describing of equilibrium when the water level gets to a certain height, you saw that with the lab experiment from last week. It reached an equilibrium. You know, the water didn't continue to accumulate inside of the apparatus we used for the jets. You know, when we were tracking the orifice, it was a tall cylinder, and there was a stream of water coming out, and there was an overflow, and then there's a jet that's going out, and then the water came in. Oh yeah, it connected here through a pipe, so it's flow in. And over time, what you saw is that the flow in was the same as the jet out plus the overflow. The water level eventually stopped rising. At first it was rising before any water was going out. At first it was rising very quickly, but then as soon as the water started going out through the jet orifice, it started slowing down a little bit. And then the jet flow was increasing as the liquid level went up. And so the liquid level is rising even more slowly because the flow out through this orifice increased. But then finally it came into equilibrium when the water level got to the overflow there. Here's another example, and before I ask you to calculate it, let's just talk about it qualitatively. So I'm going to ask for a raise of hands, and everybody has to vote. There's no abstentions in this following vote. Okay, let me describe the situation. We have a tank, and water's coming into the tank because it's being pushed through this pipe by a piston. And this piston is a big one. It has a diameter of 6 inches, and so it's a cylindrical pipe. It's sort of like a syringe. You know how a syringe, like you push the plunger into the syringe and it forces liquid one direction. So here, this piston is pushing water into the tank, and it has a velocity of v and a diameter of 6 inches. This piston is moving twice as fast as the other one, and so it's moving at 2v, but this cylindrical pipe that the piston is connected to has a diameter of 3 inches. And so here we've got a tank with flow in and flow out. So the water level, is it going to be rising, falling, or the same? That's the question. So who says that the liquid level is going to be rising? Okay, a couple of votes for rising. Who says that the liquid level is going to be falling? And who says the liquid level is going to be the same? You've all fallen victim. But not all. Many of you have fallen victim. So the liquid level isn't going to be it's not going to be the same. And so for the few of you who voted that it's not going to be the same, why is the liquid level not going to be the same? Evan, I think you were one of the votes.
Just because the diameter is higher, the diameter is the same.
Yeah. Exactly, right. Yeah, so it's like a little tricky thing, and I take pleasure in it because it's a learning moment, not because it's fun to trick you, but it's fun to teach you. So that's why I'm smirking and grinning, is because I like these little illustrations that you fall into a trap and then you say, oh, I'm never going to fall into that trap again. And so the trap here is that, just like Evan was saying, flow rate is velocity times area. And so the flow rate in is the velocity in times the cross-sectional area in. And then the Q out, likewise, is going to be the velocity out times the cross-sectional area out. All right, so the intentional trick here is to make you think that there's, like an equilibrium, because here the diameter is 6 and there the diameter is 3. But the fact of the matter is that this has 4 times the cross-sectional area. The plunger B, that plunger has 4 times the area of the plunger at A, because remember, area is pi d squared divided by 4. And so if the diameter is double, then the area is 4 times as large. Okay. So with that suggestion in your minds, the way that we can prove what's happening to the water level is just look at the flow in and the flow out. So let's do that. First of all, we want to find the area at A. So the area of piston A is just pi 3 inches squared divided by 4. So the cross-sectional area of pipe A is 7.069 square inches. And we can follow the same approach for the area at B. That's pi 6 inches squared divided by 4. So the area there is 28.274 square inches. So, like I was saying, you double the diameter, you have 4 times the cross-sectional area. So the mass flow rate in is going to be the density of the fluid times the area in and the velocity in. This fluid is water, so it has a density of 1,000 kilograms per cubic meter. And the cross-sectional area of the flow in, that is the area of B, so 28.274 inches. Now hold on a second. We've got really weird mixed units now, right? We've got density in terms of kilograms per cubic meter. We've got cross-sectional area in terms of inches. And the velocity actually doesn't have any units at all. All we know is we've got V and 2V. So I'm going to work through this problem in terms of mixed units and acknowledge that and be aware of it. But it's just a comparison. All I have to look at is the flow in versus the flow out. So I'm not ever going to know how many cubic meters per second is accumulating in there because I don't know the magnitude of V. I just know a relative indication that the velocity at A is double the velocity at B. So I'm going to proceed with these mixed units and not feel bad about it. So the velocity in is that just V. And so what I end up with is 28,274 V. And my mass flow rate out, same approach. I'm going to do the density, the area out, the velocity out. So it's 1,000 kilograms per cubic meter. My area out is that smaller 7.069 inches squared. And then the velocity, I'm going to substitute in 2V because that's what it says in the drawing. And that is, the mass flow rate out is 14,138 V. And so what's the accumulation? Accumulation is in minus out. So that's 28,274 V minus 14,138 V. So water level rising. Over time, that liquid level is going to be getting deeper. How much deeper? Depends on a couple of things. It depends on the diameter of the tank, which isn't specified, and it also depends on what's the magnitude of V. But we do know the water level is increasing. All right, this one's tricky, and I love it too because it's kind of tricky. You have a homework problem that's similar to this, although the homework problem has traditional units instead of the SI units. But what we have is, you can think of it as a pipe with water inside of it, and the cylinder that's inside here is falling down at a rate of 1 meter per second. The overall diameter of the pipe is 200 millimeters. The diameter of the cylinder is 150. And what we want to know is what's the velocity of the water that's going around this cylinder. Because in order for the cylinder to fall, it has to push water out of the way. You know, for this cylinder to go down, it has to push the water around it in order to do that. So the question is, what's the velocity of the water that's going around the cylinder if the cylinder itself falls at 1 meter per second? Okay. I'm going to have you calculate that independently, and I'll be circulating around to see how it's going, and I'll be available to answer questions as you work on it. Some problems have a trick, and the trick of this one is visualizing what does that cross-section look like that the flow is going through. I've drawn the control volume and the control surfaces over here, and so this solid cylinder, as it falls down, it's pushing water into this control volume. And since the water is being pushed into the control volume, water has to flow out of the control volume on the sides. Now, this is circular, and so a cross-sectional view makes it look like it's rectangles, but really, if we have this view now, it's clear that it's sort of like a donut situation, and saying that makes me really hungry because I'm starving right now. But the center part is the cylinder that's going down, and then the water flows around the outside of the cylinder, sort of coming at us from the whiteboard. So this is the water that's going up around the cylinder, and the cylinder falls down and pushes water into the control volume. So if I'd asked you to draw the control volume, chances are hardly anybody would have drawn this. But it turns out that this is workable because as the cylinder falls down, it's acting like a plunger, pushing the water in front of it through our control volume. So I've calculated the net area, meaning that side area on the outside of the cylinder. And here's the net area, the difference between the pipe area and the cylinder area. So 0.01374 square meters. The Reynolds transport theorem says that accumulation is in minus out. And there's no place that accumulation can occur inside of this pipe. There's no like intermediate storage tank connected to it. And so whatever flows into our control volume has to simultaneously, the same amount has to flow out. And so flow in equals flow out. And the in is dictated by the rate that the cylinder falls and the cross-sectional area of the cylinder. And so that falling cylinder pushes water into the control volume at a rate of 0.01767 cubic meters per second. And therefore, that's the same volumetric flow rate that water has to go around the sides of the cylinder and flow around that ring-shaped outside area. And if I know the net area through which the flow is exiting the control volume, I can calculate the velocity out because that's the only remaining unknown variable. So it's just V is Q divided by A. And it turns out to be 1.29 meters per second. That's the velocity that's flowing around the side. All right. Today in lab, we're going to be doing jet impact. And if you have been following the semester in your course schedule, you'll note that that's actually a revision. We were going to do the Hayes and William labs and then the jet impact, but I've actually switched them just because we're actually going to be getting to the jet impact material sooner in the semester, and a couple of other reasons that we'll get to next week when we start discussing the Hayes and Williams. But I wanted to show you some of the information about the jet impact lab. What we're going to be doing today is connecting the hydraulic bench to this inlet hose, and the inlet hose directs the flow through an orifice that has a diameter. It's on the handout that I've given you. I seem to think it's 8 millimeter jet. That's what it says here anyway. 8 millimeter jet. Okay, so And we've done this lab. Sometimes we took the lid off just to see how high in the lab the water would shoot, you know, to see if we could hit the ceiling with it. And the answer is yes, you can hit the ceiling with this fluid jet. We won't be doing that today, though. We've gotten a little bit more safety conscious over time. So the water is just going to be shooting straight out, and it's going to, the purpose of this apparatus, number one, is to make sure that we don't get splashed. You can see there's a acrylic pipe all around it, but it also is a mounting cylinder for these plastic pieces. And let me show you, there's four plastic pieces that we're going to be considering. The angles of these pieces, let's see, let me remind myself, 30 degree, 90 degree, 120, and 180. So this is the 30 degree deflection angle. So the jet that comes and impacts this plastic piece is going to have its direction changed by 30 degrees. You may be wondering, well, does it also change the velocity of the jet? And in reality, it probably does change the velocity a little bit, but we're going to be neglecting that. And we'll get into these momentum calculations next week, but just I wanted to preface, in the lab, when the jet's coming up, we'll be able to calculate the velocity of water coming out of this jet. Anybody want to have a guess on how do you know what the velocity coming out of the jet is? What's going to be your way of determining experimentally what the jet velocity is? That's right, collecting water and timing it. You guys have gotten really good at that this semester, haven't you? You got someone who you know is old reliable with a stopwatch, someone who's really good at watching the water level rise. So you're going to know the volumetric flow rate. Q is a change in volume divided by some change in time. Okay, so that's how you're going to get Q. How do you get from Q to knowing what the velocity of the jet coming out of the nozzle is? Right. So V is Q divided by area. I just told you that the diameter of the jet is 8 millimeters. So actually you don't know the diameter directly, or the jet area directly, but you know pi d squared divided by 4, and the diameter is 8 millimeters. Okay, so it all fits together. With your stopwatch and the viewing tube, you're going to be able to quantify volumetric flow rate, cross-sectional area you calculate from the known jet diameter. And so with the flow rate variation, there's a handle on the bench. It's a black handle, and you can turn the jet up and down. You'll set some jet velocity, and then you're going to find out what sort of force is generated. And when the fluid jet hits this piece, it pushes it up. And whenever I start talking about momentum in class, I ask students to visualize what happens when you stick your hand out the window as you're driving. You know, as you stick your hand out the window, if your hand is flat like this, it's a lot easier to hold your hand than if you turn your hand this way. Because when you turn your hand this way, what you're doing is you're deflecting a stream of gases. Your car is driving through the air, and the air is a fluid, and so you're essentially, the air is hitting your hand and you're causing it to go down or up. You know, it's just banging in and changing directions. But if you only have it at an angle, if you're only asking the jet of air to change its direction a little bit, it requires less force. And so this 30-degree deflector piece, it's not going to generate much force because it's not really changing the velocity all that much. It's just changing it from straight up to 30 degrees from straight up. But then when we put on the 90-degree hold on, there's two of these pieces. There's supposed to be a flat one. I must have, we've got two different sets. I didn't bring in the 90-degree deflector. But the 90-degree deflector, essentially, it screws on to the cylinder here, and the flow comes up, and it just sort of spreads it out sideways. You know, it causes the flow to change directions from completely vertical to completely horizontal. And it's generating much more of a force. And by the way that we're going to be measuring force experimentally during the lab is we're going to put this lid on here, and we're going to use these weights of known mass. This brass weight is 100 grams, and so it's in equilibrium right now. There's a spring in here that's sort of holding everything up, and I'm going to make sure that this pointer points to the silver ring. And so when there's no jet, this is in equilibrium, and so when the jet turns on, it's going to push this up, and I'll put on a certain weight, and I'll put on another weight, and then I'll adjust the flow rate. I'll adjust the flow rate until it's exactly pointing to the center silver ring that's on here. And so it'll be in equilibrium again. And so what that means is I've added a certain mass here that's equal to whatever force is generated by the jet. So the jet is basically imparting momentum to this deflector plate, and the deflector plate is translating that into an upward force that's counterbalanced by the downward force of the mass. So if you look at the data table, you'll notice all that you have to collect is what mass is added, and that's the experimental force once you multiply it by g. And then volume collected in time, that's how you're going to be able to calculate a theoretical force. The trend continues, comparing theoretical and experimental. Most of these labs through the semester, we're trying to see how good are the equations that I'm giving you. These equations like Bernoulli's equation, Reynolds number equation, momentum equation, which we'll get into next week. How good is the momentum equation? Like, does it work in the real world? If not, how big is the difference? Like, what's the percent error between the experimentally determined force that's generated and the theoretically predicted force that's generated? So there's 4 deflector plates, and things really get interesting when we start using the 120 degree deflector and 180 degree deflector. And probably calling it 180 is an exaggeration, because if it was 180, the jet would be going straight down, and this deflects it pretty well, but it's not exactly straight down. So I guess that maybe gives you something to talk about in the error, is that the 180 degree deflector is more like maybe 177 degree deflector. But we'll go over the calculations on how you actually generate, how to calculate the force, and the formulas are here on the page if you want to get a sneak peek of next week's lecture where we're headed. Basically today's experiment is just a process of adjusting the flow rate after you've added a certain amount of mass to get it back in equilibrium. And you'll notice that there's 2 runs for each of the deflector plate, kind of like medium mass and high mass. And when it comes to the 180 degree deflector, it actually generates so much force that you'll be able to put most, if not all, of these weights on here, and that still won't be enough to get it back down into equilibrium. So you'll have to reduce the flow rate to bring the jet velocity back down. So it's an enjoyable lab. This is one of the few labs, like when I have elementary school students come to see like what's hydraulics all about, what is engineering. I usually show them this one just because it's visually pretty entertaining. It's fun to play around with the jet, especially when you take the lid off, but we won't do that today. That water's nasty anyhow. So, all right, so I will see you at 2 o'clock and 3 o'clock. Again, here is the assignments if you don't remember when to come. Group B at 2 and Group A at 3.